Hello everyone. I'm extremely happy to welcome you all in the 10th webinar of PICS Today. My warm greetings to Dr. Sangyun Han. He's assistant professor in DGIST University, Korea. Dr. Han will give a talk on programmable silicon photonics. So before having this exciting topic, I would like to request Professor Vijay Krishna Das to introduce our honorable speaker. I'll also request Professor Enakshi Bhattacharya to moderate our Q&A session. Over to Professor Das.
Yeah, thank you, Diptasri. And it is our pleasure to introduce Dr. Sangyun here. And he is currently an assistant professor in Daegu Gaibuk Institute of Science and Technology, Korea. And his BS degree in electrical engineering from Seoul National University, that was in 2010. And got PhD degree in electrical engineering and computer science from the University of California, Berkeley in 2016. And from 2016 to 2020, he was a postdoctoral researcher at the physics department, KAIST, Korea. His research interests include silicon photonics, nonlinear optics, MEMS, heterogeneous integration, and of course, LiDAR. He has authored and co-authored more than 30 papers published in leading international journals and conferences. So he's a young professor in DIGST, and I think just 2 years as an assistant professor. But one of my best friend told me that he's doing very fantastic work in the programmable silicon photonics area. And it is our pleasure to, it is actually, we are grateful to him to agree giving a webinar talk in our webinar series, PICS Today webinar series. And I hope all of you will enjoy this exciting moment. I think the talk duration is about 45 minutes. And after you can keep on posting your question in Q&A box. Professor Enakshi Bhattacharya will be there at the end of the talk. She will be moderating the question and answer sessions. And if you wish, you can also directly ask question. And in the panel also, we have our colleague, other colleague, Professor Sudarshanan Srinivasan. He will be also participating in Q&A session. And our CTO, Arnab Goswami is there. So with this, I invite Dr. Sangyun. The platform is yours. And Professor Enakshi Bhattacharya also, she will be coordinating. I just hand over to all of you. Okay, thank you very much.
Okay, thank you, Dr. Krishna. Thank you for your introduction. My name is Sangyun Han. I'm currently working at DGIST, a university in Korea. Thank you for inviting me to this seminar. Actually, I have several friends I met in UC Berkeley. There was several fantastic, super intelligent Indian students. Most of them, every time I talk to Indian students, they're super smart. Yeah, so I'm very excited. Today, my topic, the topic I present is how to make a programmable photonic circuits with ultra low power by using MEMS. So my academic history, Professor Krishna has briefly mentioned. So I will just skip this. I just want to point one thing. I had a PhD in UC Berkeley under supervision of Professor Ming-Woo. So I'm a relatively new professor. I started 2020 February at DGIST. Currently, I have 7 grad students working with. And let me briefly explain the history of DGIST. So DGIST is a relatively new institution. Probably some of you heard of KAIST of Korea. So this is the most well-known one, well-known technical university in Korea. It's like similar to IIT system. So I know that IIT has a several campus around India. In Korea, we have a similar system. So we call it IST. So KAIST, DIGIST, UNIST, GIST. So there's a total 4 of them. And DIGIST has been started since 10 years ago. So it's a relatively new institution. And DIGIST has a total 5 departments. I'm in robotics and mechatronics engineering. In our department, we do robotics, and we do like a micro nano photonics, like me. We also do MEMS, and we also do biomedical research. So first topic, I will briefly, first half of the talk, I will first show you the building large-scale optical switch using MEMS. And then this was the key technology enabled for us to build a large-scale and low-power programmable photonic circuits. So let me start with a switch story. So in 2013, when I was a grad student in UC Berkeley under supervision of Professor Ming Wu, we were at that time, still data centers are growing, but at that time, we are experiencing booming up of data IP traffic in data center. So the Cisco, every year they report global cloud index, and it expected that every 5 years, the data IP traffic in data center triples, meaning in 10 years is almost 10 times larger every 10 years. So probably now this kind of chart is quite familiar with you. So currently 2018, the data center, because the data traffic is so large, they're consuming 1% of worldwide electricity. And if this trend keeps up, if the engineers doesn't work hard enough, then by 2030, the data center will use up 8% of global electricity. So we should keep working hard. If we look into data center, the interesting thing is that the traffic data center generates, the 70 of them are actually just go around inside of data center. They never goes out. So in order to have an efficient data center, we first look into how to manage the circulation of data inside of data center between the servers. So if you look into data centers, the left figure shows the simplified picture of how data center look like. It has many servers. For example, the Amazon data center at Dublin, they have 100K servers, and these servers are linked through optical links, which means optical fibers. And these optical fibers, they are connected through switches with a few hierarchies. And these switches has like 10,000s of them in the data center. And the interesting thing is that they're using optical links, which is optical fiber, but they're using electrical switch to switch these optical fibers. So this is intuitively awkward because you increase the bandwidth by using optical links, but now you're decreasing down the bandwidth by using the electrical switch. So for doing that, you need the optical transceivers, which convert optical signal into electrical signal or electric signal into optical signal. So this adds you additional budget to buy the transceivers and adds you additional power consumption. So in data center, there are actually millions of them. So this is intuitively not a pretty picture, but why people are using electrical switch instead of optical switch. The reason is that the optical switch you can buy at the market at this moment is not sufficiently powerful for data centers. They're actually quite mature technology. In early 2000, when there was an internet boom, was internet bubble era, people have been developing these optical switches, and they're still selling in the market. They have large port count, such as more than a few hundred ports, and the insertion loss, it could be less than 3 dB. So this is wonderful. However, the working principle of this optical switch is using a moving MEMS mirror, and therefore the switching speed is only a few tens of milliseconds. So meaning that when they do switching, so many traffics there's a dead time for the switching. In addition to that, the optical switches are very expensive. If you divide so for example, this one optical switch, you need to pay a few tens of K US dollar. If you divide the cost by number of ports, you're paying about $100 per port. So as I mentioned in the previous slide, you need 50K of switches. Then budget-wise, this is very, very expensive. So probably most of you are familiar with the silicon photonics. So people working on silicon photonics or integrated optics are I remember it was like since mid 2000 or early 2010, people now are thinking of building this optical switch into small silicon chip or other integrated optics chip. That way they can make it faster, cheaper, and potentially higher performance in many metrics. So by integrating the switches into a silicon chip, it was quite successful in terms of integration. They could integrate the optical switch with electronic driving circuit on the same chip, and speed was quite fast compared to tens of milliseconds of MEMS mirror switch. These silicon photonic switches go down to microsecond, or if you pay a lot of loss, then you can even go down to nanosecond. However, the problem of these switches was not very scalable. So if you plot the optical loss of these switches per port, then you can get this type of plot. So roughly you have between 0.2 to 0.5 dB per port. So meaning that if you have more than 100 port, you have a few tens of like 20 to 50 dB of loss, which is very detrimental for optical communication in terms of signal to noise ratio. So from here on, I will show you, we added MEMS, not the old-fashioned mirror MEMS, but we add MEMS to waveguides to increase the port of optical switch, integrated silicon photonic switch by a large amount. And the optical loss per port will reduce roughly 10 times compared to other conventional silicon photonic switches. So at this moment, this point is, so I was participating up to this point when I was grad student in Berkeley. And after I left, Dr. Taejun Seok, who now started the startup company using this technology, he developed 240 by 240 silicon photonic switch, which is the largest number of port ever reported in the integrated optics based optical switch. So there's a huge gap between huge improvement by using MEMS, waveguide attached MEMS. So what are the difference between the conventional silicon photonic switches and the silicon photonic switch we developed at Berkeley, which use MEMS to move waveguide? So this slide shows you the conventional silicon photonic switches, how they works. They basically have some sort of topology. Here I draw a matrix topology. You can have several of them, but simplifying, you can draw something like this. And each cross point of the mesh, you have a sort of a Mahagender interferometer, something like this. So probably I heard that 80% of the audience are photonics, has photonics background. So most of you know what the Mahagender interferometer is. So basically, they have two arms and two inputs and two outputs. And by varying the one path, optical path of one path, then you can change the interference condition and you can route the light either to the top or to the bottom. And this is the silicon photonics version of the MZI. It's very similar to, is basically same physical implementation as, same physical principle as the free space one. So in silicon photonics switches, conventional ones, has this type of waveguide based MZIs in each these mesh points. However, the issue was that if you, sorry, the issue is that if you increase the number of port, then the light need to go through many of these meshes. And by going through these meshes, this is not free. Every time you go through one mesh, the light is experiencing MZI, and then each MZI is about 0.2 dB. So if you increase the number of port, light need to go through more of mesh, so optical loss increase proportionally. In addition, this MZI, when you change the path length, they use a thermal heater. So one thermal heater consumes tens of milliwatt, not the whole chip, but just one heater. So this chip is really, really hot. I'll compare how hot this chip is in the coming slide, but it's super hot. So in terms of energy consumption, this is not very efficient. So in this slide, I will show you how Berkeley we did to build a switch on silicon photonics platform. So we has a waveguide mesh, but now instead of using MZI or thermal heater, we use a moving optical waveguide. So this one is enlarged in here. So we add MEMS actuator to waveguide, and by doing that, we can control the vertical position of the waveguide. So when the waveguide is up, when the waveguide is up, then light just go through. But when we apply voltage to pull the waveguide down, then light change the direction. So this is how we do switching. So by doing this, regardless of how many ports you have, light only need to go through one switching because light only need to bend once, right? So the optical loss doesn't increase as much as the MZI-based architecture. So this way we could increase port to large amount without too much loss penalty. In addition to that, this actuator is actuated by electrostatic fashion, meaning that there's no current flow once the actuator is moved to a certain position. So unless there's a few leaks current through the dielectric, but that's really small amount. So the static power consumption of this actuator is 10 femtowatt compared to the thermal heater. This is 10 to the 12th times of reduction. So this is a huge improvement also in terms of electrical power consumption. So this kind of a low loss and low power consumption is the key to build a large scale and ultra low loss, ultra low power programmable photonic circuit. I will show you in the next half part of this presentation. Yeah. So we had gone through several versions of this optical switch using MEMS actuated waveguides. And the left table in the table, I showed comparison. The left one is the our Berkeley technology we developed at Berkeley. The right one is the thermal optic based switch. So in terms of port count or optical loss or crosstalk, nearly every matrix is better than the conventional thermal optic based silicon photonic switch. One drawback is the high voltage. So because the MEMS actuator, we need to move 1 micron with high speed. We need to apply between 10 to 40 volt, but there is a trade-off. So if you give up the speed a little bit, then you can reduce the voltage to few volt. But at this moment, we're having about 1 microsecond speed, which is actually a little bit faster than thermal optic. So we are paying high voltage. So other than voltage, all the metrics of this MEMS-based silicon photonic switch are superior. So this is the chip image. This was second version. And as you can see, this blue colored waveguide is the actuated waveguide, which moving up and down. And this red waveguide, which is the bottom matrix crossbar. So when you apply voltage, this blue waveguide moves up and down. So the speed, as I mentioned, it goes roughly 1 microsecond of actuation time, which is actually when I say this is MEMS actuated, then people have two questions. One is, oh, is it maybe slow? And two is is it reliable? And both answer, I can say yes. So left graph shows that this is actually quite fast. So it goes below 1 microsecond of response time on and off. Compared to thermal optics, I've seen thermal optic switch. The fastest one I've seen like 2 microsecond, but that's really outlier. Most of them are like tens of 10 microsecond-ish. So, but this is actually slower than electro-optic switches. But however, as you may know, electro-optics one has high optical loss, so it's not really scalable. And this is 1,000 times faster than previous MEMS mirror-based switch. And in terms of reliability, we could run it more than 10 billion cycles. Actually, we didn't do more, not because switch is broken, switch was still working, but we thought that 10 billion cycle was good enough to show that this is reliable. So this is the switch based on MEMS technology I've developed. I've participated in developing in Berkeley. Using this technology, when I joined DGIST 2 years ago, I started to thinking of building programmable photonic circuits. So I'll move to that part. So I'll just skip this. Yeah. So so nowadays people are talking about programmable photonic circuits. Some people are even called this field programmable photonic gate array, just like FPGA in electronics. So I assume most of you know what FPGA is, like which is like programmable for programmable circuits. So you can program it, and that circuit become whatever you programmed it. So that's like multi-purpose circuits, so you can say. So if we compare the history of the electronics and photonics in terms of scaling, the left graph shows the scaling of electronics, which is Moore's law. Most of you are super familiar with it. So Moore's law, although is almost end of Moore's law, engineers like still doing good. So I believe a few weeks ago, Samsung announced that they start to manufacture 3 nanometer gate length transistors. So nowadays, per chip, you have about 10 to the 10 transistors. But if you look back early 1980s, there's only 10 to the 5 elements per chips. And if you look at the photonics, is relatively late than the electronics. And however, it's catching up quite fast with an exponential trend. So nowadays, the largest number of element per chip is 10 to the 5 in photonics. Actually, this point is made by our team at Berkeley, made by the optical switch, which was 240 by 240 ports. So that's the point. So if you look back to electronics, what happened when they 10 to the 5 per chip, which is 1980s, there was first commercial FPGA, which was sold by Xilinx, which is one of the most famous company for making still one of the most famous company selling FPGA. At that time, the gate was only 800, and this was the first commercial. You can buy commercial, I mean you can buy in the market. Oh, sorry, there was a question. Sorry. I just saw the chat was on. Should I read that now, or should I
We can
read
do it
that?
at the end, but he referred to this slide 21. We can do it at the end. Please carry on.
Okay, thank you. Yeah. Okay, so I'll continue. So yeah, there was the beginning of FPGA. So nowadays, I don't know, it's really just there's a magic. The 10 to the 5 is a magic number or just coincidence, but a few years from now, people think in photonics community, people thinking of building similar to FPGA in photonics version. So the concept of programmable photonic circuit was started with a programmable RF photonic filter. The pioneer of this area is Professor Jose Kemeny in Italia. In Spain. The concept was that just looking very similar to FPGA in electronics. So you make an identical waveguide mesh, and at mesh, each edge of the mesh, you put a optical switch in addition to optical phase shifters. Here, by using by controlling optical switch and optical phase shifters, you can route the light wherever you route the light as you want. So for example, if you program it right, you can make a Mahagender filter, or in other words, a finite impulse response filter, optical RF filter. Or if you program another way, then you can synthesize ring filter, or in other words, infinite impulse response filter. So the basic, the core concept is you have identical this 2x2 switch. Actually, this is not just more than 2x2 switch. This 2x2 switch plus optical phase shifter, because light has a phase information, whereas the electronic current doesn't have it. So electric current, you only need to switch to make a programmable circuit, but light, you also need to control the phase. So that's why you need phase shifter here in addition to optical switch. So basically, you have many of them in identical fashion, and then the user program it as he wants to, whatever filter he wants to synthesize. And then people even evolve this concept further. Now people thinking of using this concept not only to just RF photonic processing. However, on the other hand, people thinking of using this just like FPGA in electronics, just a general photonic circuits. So just a user buy it, and he just program it using computer software, and whatever he programs it, it becomes what he programs it. So, but however, this is not really realized yet. This is what really people are imagining at this point. Right now, this is conceptualized and people are working on it, but we are not at this mature stage. But this is, I'm just saying, this is concept, what people want to do in few years. Let's come back to the waveguide mesh. In waveguide mesh, I mentioned that at each edge, there was an optical switch and phase shifter. In more rigorous term, we call it optical gate. What optical gate look like is that, as I mentioned, there's a 2x2 tunable coupler, which is like analog switch. So you can mix the light from 2 inputs to 2 outputs. You can control the amount of light from this input to this input, this output, this input, this output, and this input to this output, and this input to this output. So this is really analog switch. In addition to that, you have one phase shifter to control the relative phase between these two outputs. So this makes up one optical gate, and this is sitting in each edge of this waveguide mesh. So then now the key is now then you make a so large scale programmable photonic circuit. So in programmability, really when it becomes powerful is when you have a large programmability. Large programmability means that you need to large number of gates. As I'm showing earlier, the first commercialized FPGA Xilinx sold it has 880 gates. So I also assume that in order to this kind of photonic program circuit concept to be commercially useful, we also want to aim at numbers. But in the coming slide, I'll show you that we are still far, far behind that number. Okay, so now then I said we need to have many of them. So large number of gates means powerful software, powerful programmable photonic circuits. So what do you need is that you need to have these two components, very low loss, meaning low optical loss, because light needs to go through many of them. Then unlike the electronic wire, waveguide, optical waveguide has optical loss, so you need to go through many of them, you're losing light. So in order to have a large number of gates, you need to have a low loss. In addition to that, you need to have a very low electrical power in order to control densely packed these optical gates. So this slide is a little bit of a side story. So people also, when they are using optical gate, they cascade the optical gate. People realize that this can be a matrix multiplication. You can do matrix multiplication using light. So some people using this cascade optical gate to do matrix multiplication, or even people doing machine learning. But this is just other side of the story, so I'll just quickly go through this, just go over this. So now coming back to the optical gate, as I mentioned earlier, optical gate has two parts. One is the tunable coupler, the other is phase shifter. So let me first explain the phase shifter part. So I always assume that most of you know how to make an optical phase shifter using waveguide. So basically, the most popular way of making it is you put a heater on top of waveguide, just like this, or if you look at the cross-section view like this. Then when you flow the current through heater, then heater heats up, and then this heats goes to the waveguide, then waveguide heats up, temperature goes up, then index change, then which makes the optical pathing longer. So this is how usually people make the optical phase shifter using waveguide. However, this optical phase shifter, it consumes large power, which is the per phase shifter, it consumes at least 10 milliwatt, or even some are tens of milliwatt. And there is another way people developing using other than thermal way. For example, piezo. People press waveguide, give pressure to waveguide by using piezo material to change the refractive index. However, the length is like a centimeter long. So there's not a good, not a satisfying option for phase shifter for programmable photonic circuit at this moment. And tunable coupler, also how they build is, this is very similar to silicon photonic switch architecture. I'll show you, I have shown in the first part of the switch part. So in this switch, you also have phase shifter. So it has same problem. It has a high power consumption. And if it's not high power, then you need a very long length. So at last, because this is, as I mentioned, this is equivalently same as MZI. And probably you know that because it's interferometer, if this beam splitter, or this is beam splitter, is not perfectly 50-50, then there's always leakage, even though you wanna, even though you had the perfect phase condition. So this is very difficult to achieve, meaning perfect beam splitter is very difficult to make in waveguide. So this give you leakage, or in other words, optical loss. So this is the problem of current optical gates. So let me show you a funny picture here. So as I mentioned, phase shifter based on thermal tuning, they consume 10 milliwatt per phase shifter at least. This power density, actually, it's larger than the electric cooker you can buy, you use in your kitchen. So your kitchen. So if you use the thermal phase shifter, the power density is roughly 1000 watt per centimeter square. So this is like just harder than your electric cooker. So you cannot really scale them. So yeah, you may question that, there's many other ways of having optical phase shifter other than thermal phase shifter. But yes, but these other options I listed here are not actually good for large scale devices. They're fast. For example, 3.5 on silicon or lithium niobate, which is really popular since a few years ago, and also piezo way of changing. There's a piezo way of doing it. The speed are quite fast, like they can even go tens of gigahertz. However, the length is really long, millimeter to centimeter. Compared to thermal phase shifter, they can reduce down to 100 micron. So this is roughly 10 or 100 times longer. In terms of area, it's squares, so you can only have few of them in per chip. So I mean, this is awesome works, but this is application-wise, this is not made for large-scale devices. In addition to that, optical loss is high. And recently, MIT, they reported silicon nitride based. They put piezo material near silicon nitride waveguide, and they push and they give pressure to change the refractive index. However, the length is again very long, and optical loss is very high. So one phase shifter, you're paying 3.5 dB of optical loss. So these are actually, at least at this moment, this performance is not scalable. So coming back to this plot, as I mentioned, the world record of number of elements per chip in photonics is made by our team at Berkeley using a silicon photonic MEMS switch, silicon photonic MEMS switch. So I've started making the optical gate, which is the basic building block for programmable photonic circuits using MEMS. So basically, we use waveguides. So to remind you, we need two components. One is tunable coupler, the other is phase shifter. This slide shows you the tunable coupler part. So basically, this simply shows how it works. So this is waveguide. So when this waveguide is up, then light just go through. When this is down, light jump to the other waveguide. And when this waveguide is in the middle, then light splits. So by controlling the distance between these two waveguides, you can control the coupling, so meaning tunable coupling. And so this is the actual SEM image of the gate. By cascading them, you can make an N-by-N matrix multiplier. We have 3 by having 3 of them cascaded. And this is the device picture. Sorry, this was I borrowed from Clio. So we present this work at Clio this year. And the fabrication of the chip was done in 8-inch SOI wafer level fabrication facility in Korea. And this MEMS device, you may wonder, oh, are they reliable? Sorry, are they fabrication of them are compatible with this CMOS or other silicon photonic devices? I would say yes, because in the same wafer, like in this area, we had PIN high-speed modulator, silicon modulators, and other silicon thermal optic based devices. So this is quite compatible to standard silicon photonic process. So in terms of reliability, again, it's MEMS, so you may wonder, but we've measured 10 to the 9 cycles and still doesn't show drift in performance, both in tunable coupler and phase shifter. The reason, then I'll just skip this slide. So here, this is our recent version is under review, so I cannot give you too much detail on this device. But the right one is the most state-of-art programmable photonic circuits, experimental one, published so far. It has, as you can see, 7 meshes. It's a hexagonal mesh, so it has, I think, how many gates? Yeah, so each edge is gates, and basically has 7 meshes. And in digits, and by the way, this is thermal way, so it's consume large power, and there's thermal crosstalk, so they couldn't pack it more tightly. But in MEMS way, we develop it digist. So this is actual area scale, so in scale. So with much smaller area, we build a 30 mesh with a much low power consumption. So this is under review. Maybe I hope this will be published in a few months. So at this moment, I cannot reveal too much detail, but I can show you our previous version of this programmable photonic circuits. So this one we reported in Clio 2021, and this one we didn't have phase shifter. This one only had a tunable coupler, so it's not really fully functional field programmable photonic gate array. But this shows the potential. This showed the potential of full functioning FPGA photonic field programmable photonic gate array. So as you can see, this is video. This is tunable coupler moving up and down. We apply voltage on and off slowly, and we record it with video. So basically, we have 16 cells. Again, this doesn't have phase shifter, so it's not a complete programmable photonic circuit, but this is the early version of our device based on MEMS. So using that device, we programmed like a single ring filter with variable extinction ratio, and like double ring filter. Now you can filter two wavelengths, like EDRA filter and like a 4-ring crow. You can program. This is experimental way. And this is another programmable photonic, another type of programmable photonic circuit. So Mahagender interferometer actually the Mahagender I've shown you in earlier, or most of Mahagender, you only have 2 pi phase shift. Okay. Oh, sorry. I just look at the note. I'll answer all the questions at the end of my presentation. However, this one basic idea is that you make a tunable delay line. So depends on which tunable coupler you turning on. You can make a different delay path. Therefore, you can make a different unbalanced lengths of your MZI. So in this way, this kind of tunable delay line has many applications in RF photonics. Especially, I'm applying this for radar, not LiDAR, radar signal processing. People have found this is useful for optical signal processing for radar applications. Yeah. So, and another one is that by using the tunable coupler based on MEMS, we have built a programmable beam pattern generator. So basic idea is that, so this is kind of a beam scanner, but not OPA. OPA is you emit light through all the grating coupler at the same time, and you just change the relative phase between them. But here, this is called the focal plane switch array concept. This concept we didn't develop, but we developed it using MEMS. This is our contribution, developed based on MEMS. So here you put tunable couplers, and in the tunable couplers, you connect the waveguide, and this waveguide is connected to each grating couplers. So by turning on the switch or turning on the amount of turning on, then you can send the light to each grating coupler, which one you want. And then you put lens on top of this chip with the focal length distance. Then the beam is collimated and emit to the space. So this emission angle or steering angle depends on the location of the grating coupler. So by controlling those couplers, we emit light to all the angles or some partial angles, or even we can draw arbitrarily, we can emit light arbitrary angle. So one thing I want to point out is that this is not consecutively recorded. This is emitting all the at the same time. So LiDAR, OPA, optical phase array, this is really difficult for do, right? You cannot really make a multi-beam pattern generation, but by using this tunable coupler connected to grating coupler, you can do this. And last one, here we put tunable coupler and one circular loop, then we can make a Saginaw loop, tunable reflector. So this is published in Clio 2021. So by just applying voltage to tunable coupler with femtowatt static power, you can have 100%, 0 to 100% reflectivity. This is my last slide. Take-home message I would like to give you is that by using MEMS, you can do compact, very low loss, and ultra low power operation of programmable photonic circuits, and you can have a large degree of freedom to build many types of programmable photonic circuits. Thank you for listening.
Thank you very much for that very interesting talk, Sangun. There are quite a few questions. Bijoy, can we start with the questions?
Sure. Let me open up the chat.
Yeah, can I say? Yeah.
Yeah. So, Sangun, can you see the Q&A? The first
Yeah.
question is legend on slide 21.
Oh,
Is it correct?
Actually, I only see two questions. So
Yeah. So I'll read them out. If you go to slide 21.
Sure. '21.
No, I think where you first introduced. Yeah.
I think
Yes.
this
Yeah.
one.
Yeah. The one.
How
This is
many?
19. 19. This is 19. The one you just showed, 21. If you see below. So where you show the actuation.
Yeah.
So the
You mean,
question is if the legend is reversed. Yeah, not this one. Where you show the actuation of the MEMS. You actually just showed that slide a few minutes back.
Okay, let me do this. So which one? 19, 20, 21.
Yeah, 21 is not the correct number that he's given. Yeah, I think it is this 17.
17.
Yeah.
Okay.
So he's asking between on and off,
Okay.
whether it is correct, the legend is correct, the caption is correct.
Yeah. Yeah. So yeah, caption is correct. So on means this. So waveguide is down, up is off, down is on. So on means light goes through this moving coupler, and off means light goes to just through the matrix waveguide.
Okay. Yeah, I thought you meant also the actuation, right? That's when it's actuated down, the
Yeah.
on state. Yeah.
Right. Right.
There's a question from Ashutosh. Can you please comment on the footprint requirement for MEMS-based optical switches?
Footprint. Okay, that's a good question. So one cell, unit cell size is roughly 100 by 100 micron. So maybe related to that, I skipped this, but this is kind of interesting picture. So this is the 240 by 240 switch made by Dr. Taejun Suk. So you need roughly 3 centimeter by 3 centimeter for switch, like switch area, and rest of them are like grading couplers and other preferred. Yeah.
Okay.
Yeah. So one cell is roughly 100 by 100 micrometer square.
Yeah. The next question is what kind of electronic driver have you used to drive the 240 by 240 switch architecture? Well, at Berkeley, what did they use?
Okay, that's a very good question. So actually for 240 by 240, I wasn't participated in, but for the the older version, actually we so by the time I was in Berkeley, we just use a DC power supply or sometimes function generator. So probably the question is related to, can you actually drive all of them at the same time? The answer is no. So this is really at research level, we probe them one by one, but one thing I want to show you that this is really you don't one thing I really show you is let me show you this device. Let me is it? So the thing is that you may worry that because 240 by 240, there's number of pads or 240 square. So how are you gonna address all of them all of them? So there was issue. So we didn't fully connect them at research level, but let me show you. But later on, we developed a row column addressing scheme. So meaning that 240 by 240 cells, you only need so 240 times 2, not 240 square. So which makes much better. So probably electrical row column addressing scheme you may familiar with. That's what we were developing for. Yeah.
And a light question from the same person is because each switch needs at least 10 to 40 volts from the supply. So what are the challenges, to drive so many switches?
Yes, yes. So it is a very good question. So actually nowadays CMOS, when we talk to the circuit designers, CMOS circuit designers, they only even like 10 volts is really high for them. So it is very difficult for them. I mean, it's old technology that if you want to have a higher voltage. So we actually it is problematic to have a large number of channels for such high voltages. So again, we didn't make the driver yet. Yeah.
So a third question from the same person, Kumar Piyush, is GST based or GSST based phase shifters are as power efficient as the MEMS based ones you just described. So how are the MEMS ones better than those?
Okay, that's also a very good question. So actually, recently I've read some recent phase change material-based optical phase shifter. So static power-wise, they don't consume power. It's obvious because once you change the state, then you just memorize the state. However, they can only if you turn on and off like 1,000 times, they're already broken. So reliability-wise, they are not really at the level of commercialized or even at research level. 1,000 times, you just broke your device. And second, the energy take to switching the state is actually larger than MEMS. So our MEMS device take less energy to changing the state than the phase change material. I remember it was few orders of magnitude difference.
There are a few questions on fabrication. I'll put them together. One is on can you comment on the fabrication complexity difference between MEMS based and simple optical waveguide? And the second one is how many extra fabrication steps are required in addition to a standard SOI process steps? Are there any other materials used involved in the fabrication?
Okay, that's a very good question. So there is two extreme versions of these MEMS devices. One extreme version, actually I myself fabricated from beginning to end. I use 20 masks. That one I didn't show you here, but this one is the device. So this one is extremely difficult to fabricate. I use 20 masks. So if you look at the 3D structure of it, it looks like this. So here but material-wise, it's not really exotic. Material here used is just silicon dioxide, polysilicon. And maybe one exotic material you may feel exotic is aluminum oxide. So other than that, it's just standard CMOS. And the process stepwise, it's just deposition and etching, lithography, and maybe one wafer bonding for this extreme case. But is other than wafer bonding, is really just CMOS compatible. And one more thing, the HF vapor release to etch off this sacrificial layer so that MEMS get float in the air. So this is done at the very last step. Everything is done. At the very last step, we put the chip into a HU vapor machine. Then the chip is done. So this doesn't really conflict with CMOS process. So this is a very extreme case. And the simple case is the
Phase shifter, maybe.
right, phase shifter and this tunable coupler. Yes, exactly. So this is just a 3-step, just SOI wafer. You just do 3-step silicon etch just to make your waveguide and actuator, and then you put it into HF vapor machine, then done. So this doesn't have any.
So Sanguine, is this a hinge? The movement, is it a hinge? Is there a hinge involved here in this?
Yes. So this is hinge. Yeah.
Okay. And you know, the previous slide you showed one in green, one in orange, but they're the same material, right? Just the slide before this, the schematic.
This
Yeah,
one?
they're the same
This
material.
I just colored, but all silicon.
Yeah,
all
it's
crystal
okay.
silicon. Yeah.
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 Okay. So the phase shifter is simpler, but the full gate may be more complicated. And then there's a question on heat dissipation. What about the heat dissipation? I don't think
Yes.
there's that much of a problem, is it?
Right. So as I show in this graph, so this device only consume like femtowatt. So it's not really generating nearly no heat.
Okay, there are a few more questions in chat, not in QA. Let me open that. How many extra fabrication steps are required? That's the same question. And what is the gap between MEMS electrodes for your targeted 1 micron deformation? Actually, I wanted to ask that too. What is the gap between the electrodes for 1 micron deformation?
Okay, so for tunable coupler, I guess. So this is the detailed structure. So let me just zoom this up. Is this clear for you? So,
Yeah, but the gap is not, it doesn't give you the gap here. Oh, is that 2 micron is the gap?
Oh yeah, 2 micron is the
Okay.
So this is gap between the device layer and the substrate. But actually what's moving is what's moving is this one. So this one is going up and down this way.
What is that gap?
1 micron.
That's 1 micron. Okay.
Yeah.
That's a torsional movement anyway.
Roughly, yes.
Angular, yeah.
Right.
Yeah, well, I think we've come to the end of questions. Can I ask a few questions, one or two? So some of them were answered. What about the transient power? I understand for MEMS electrostatic actuation, your static power is low. What is there a transient power?
Sure. Let me see if I have the graph. So I was show you this graph. So tuning energy means in total power, total energy you put into the actuator to approach a certain state. So this is tens of picojoule.
Okay.
Yeah.
Low enough. This is there, you're not dissipating too much energy, but the ambient temperature, will it have an effect? Temperature dependence on the structure, phase shifter, because very small movements are important. Yeah.
Yes, that's actually also a very critical question. So we haven't tested the temperature dependence yet. However, we are assuming that this should be less depends on temperature compared to thermal optic or other effect-based ones, because as I mentioned earlier, thermal optic coefficient or electro-optic coefficient are really small. So they're really small effect. So ambient temperature change is relatively not negligible to this small effect. But MEMS, you're actually creating large effect by just changing geometry. So it should be less susceptible.
Okay. And then finally, I mean, you have been using electrostatic and that's easier to design everything, but you do use some piezoelectric material. What are your comments on actuation using piezoelectric instead of electrostatic?
Okay. So for piezo, I think it's a good option. It has a stronger force and maybe somewhat faster, but it requires exotic material, and it requires, meaning exotic material means more complicated process. So and the benefit it's not huge compared to just silicon electrostatic.
Electrostatic. Okay.
Right. Right.
That was wonderful, Sangyun. And we have a center for MEMS and nanophotonics. So maybe now the two can come together thanks to your talk.
And actually, one question for
yes, I was just going to open it for everyone. Yeah.
So I think the same Biman Chattopadhyay, I think he's from Confluence, Bangalore. He's asking another question. Can you see that? Is the
Is
control?
it in Q&A or in chat?
What is the gap?
Yeah, it's in Q&A. Okay.
Capacitance of the control. What is the capacitance of the control structure which has to be
charged and discharged for the actuation?
Sorry, could you repeat again?
Yeah,
I don't see
I'll
on the
repeat
chat.
it.
Yeah.
What is the capacitance of the control structure which has to be charged and discharged for actuation?
Okay, that's a very good question. So I don't have the number on top of my head. Sorry, I don't have that on top of my head.
And there is another question from him. Is the control voltage to coupling ratio relationship linear? Probably not.
No. So it's a good question. So this curve shows you voltage. This is in dB scale, or this in linear scale. So you can see this sort of non-linear. So nothing happens until 8 volt, and suddenly something happens. Yeah. Yeah. So this is, you apply voltage, but the field is exponential decay. So until some point, there's actually negligible optical effect, and after that, actually, waveguides sees each other.
Right.
Yeah. So I have one related question. So Sangur, it's an excellent talk. I think just thoroughly enjoyed. So one question that you said that this switching voltage ranging from 10 to 40 volt, right? So does it mean that your yield of the devices are not good?
Yield is nearly perfect. So high voltage doesn't means, I mean, your question was that
why you are saying the range of voltage, switching voltage, for example, you consider just like a V-Pi or something like that, a single voltage. It should be just a little variation.
Okay, so maybe it was a little bit misleading. So the reason I said 10 to the 40 is not the variation of one model. We have
the design.
several designs, several versions.
Yeah.
I see. Okay.
Yeah.
All right. Okay. So your wafer, you have a full wafer run in your national nano center, right? It is in KAIST. That is
in KAIST, yes.
So wafer scale yield is how much you get?
This is perfect.
You mean yield?
It's a 90% or wafer scale yield.
So actually, we didn't really study the yield. We just pick a chip and working good, then we just proceed.
Best device you characterize it.
But I mean, so if one wafer turns out okay, then the whole wafer is good. So
I see.
Yeah.
Okay. And so one question, I think you answered that this phase change material, that after 1,000 times it breaks, you said. But I think that these phase change materials are widely used in memory applications. Is that similar problem there as well, you mean?
So, so I don't know about the electronics part, but the photonics, I'm not 100% sure why photonic optical phase shifters, the durability is so low. But that's what we see in most recent papers. But I don't believe that that's fundamental limit. Maybe they do more advanced packaging or more material science, they can do better. But what I was mentioning was just at this moment, like 2022, that's what photonics community has.
Okay. Okay, I am done. That's a very good talk. And also, I just take this opportunity. If we invite you, you please visit us. We have a very good facility, as Professor Enakshi Bhattacharya said. So all these MEMS related structures we can fabricate in house here also. So maybe your collaboration would help us a lot.
So let me. So I never visit India, but I really want to visit because let me quickly. So I practice yoga.
So you must be looking for going to North Himalaya probably.
No, there are yoga centers here also.
So let me show you just 30 seconds. Let me show you how I practice. Yeah. So this is me.
Good with mask, yeah?
And with a mask, right?
Excellent, yeah.
So every morning I do this.
In the lab.
Or in my home. I wake up, do yoga, and go to lab.
Great.
Very good.
So please come
Yeah.
we'll invite you and we'll be very happy to host you here.
Sure.
Thank you very much. Yeah.
So
So
maybe
Vijay, can we close now?
Sudarshan is there? Maybe he has some question? No, it left. I think, yeah.
Pardon me?
No, I'm just asking another. Sudarshan is there. Do you have any
Yes,
question?
he's there.
Yeah, no, thanks again, Sangyun. I've been following the work from Professor Wu and yourself for a long time. So, we know you guys do some impressive work there. So,
Thank you very much. Yeah. Thank you for inviting me today.
Yeah. Thank you very much. Yeah. We can close then. Yeah, please.
Okay, thank you very much. Bye-bye.
Yeah. Bye-bye.
And to say maybe all the participants, you can just you have some words for participants.
Oh,
Yeah, okay, so thank you, Dr. Han, for your wonderful presentation. And thank you, Professor Bhattacharya, for handling our Q&A session very nicely. And finally, my heartful thanks to all the participants. So I hope to see you all in our next webinar in October. Okay, have a nice evening.
Yeah.
Okay.
Bye.
Thank you very much. Bye-bye.
Bye.